Start recording. All right, so we've been on a little bit of a break, and so what we want to do is we are going to have a little bit of revision, and then we're going to basically this is going to be sort of like I thought that last session we had was really useful, and so I wanted to do a full-on round of revision on that and expand on it a little bit. So does that sound good to you?
Yeah, I don't remember. I know that it was useful. I remember learning quite a little bit about bit shifting, and now I think I've forgotten all of it. So,
Well,
yeah, review would be great.
That's excellent. Okay. Well, excellent. That review is great. Let's start. Okay, so I just wanted to start with a little bit of theory first. So I'm just going to start peeling pages over from Wikipedia. So we talked about the Pigeonhole Principle, and it's pretty simple. It's like if you have 10 pigeons and 9 holes, you're going to have to double up on a hole. And it's sort of the mathematical principle behind hashing, in a sense. Like if we have 9 possible hashes and we want to insert 10 items into, like if we want to hash 10 items, we're guaranteed to have a collision. So does that make sense?
Yep, absolutely.
Yeah, so that's pretty straightforward. The next thing to look at is something called the birthday problem. And basically this is how you calculate the likelihood of a collision. So I want to just go through a quick example before we sort of look at the page too much. So let's say we have 2 bits. We've got bit A and B, let's say, and 0, 0, 0, 1, 1, 0, 1, 1. And there's 4 possible combinations of these 2 bits. That should be sort of fairly straightforward. So that tells us we have 1, 2, 3, 4 pigeonholes, effectively. So 4 outputs that the hash value can be. And so we want to calculate the odds of a collision. So we're going to insert our first pigeon. So we're going to say we have a pigeon. And we're going to hash that pigeon. And it's going to end up in one of these 4 holes. Now, the thing about the hash function is it's basically a pseudo-random number generator. If you've chosen a good hash and implemented it well. So it's pretty much random which of these buckets the pigeon will fall in. So say it falls into bucket number 2.
Right.
For our purposes, because it's random, we can basically pretend that it's fallen into bucket 1. Not because we've moved it to bucket 1, but because we've actually swapped bucket 1 and 2, or 0 and 1.
Right.
Because the buckets are arbitrary. So, if we've swapped them, maybe this is still 0, 1, and that's now 0, 0, and then 1, 0, 1, 1, or whatever. So swapping them conceptually is sort of a non-issue. So we start with our pigeon, and it's like, what are the odds that it's collided here? We've got a 0% chance of collision, a 100% chance of not collision, because obviously it's empty. So now we're going to insert pigeon number 2.
So it looks like a cannon.
Yep. So he could end up here, but by the same principle, we just
sure, you can swap that for your own.
Here.
Yeah.
But he could also end up here when we hash him. So there's nothing in the hash function that prevents the two colliding like that. So
Right.
there's effectively two places our pigeon could end up.
Right. Any of the other buckets is position 1 that we've swapped, and then the other position is the one we already have.
Yeah. So this is going to be 25% chance down this way, and this is a 75% chance this way.
Right.
So let's draw that a bit better. Now where it gets a little bit interesting is, okay, so now we want to insert pigeon number 3. So he could end up anywhere here or here or here. And so what we've ended up with, keep color coding these, so probably not that much point color coding these, but we'll do it anyway. So what's going to happen is there's now a 50-50% chance that he's going to collide. So our thing looks like this. So
Oh, interesting. It was 75 before, but it's only 50 now.
yes.
I thought it would be 75 the other way. Interesting. Okay.
So and hopefully you can see that from the diagram. So there's a 25% chance he ends up in blue's home. Oh, hang on. Have I made a mistake here? I have. I'm pretty sure I have. Oh, okay. So this is yeah, like there's a subtlety here that I was getting to, and it's like the diagram is not conducive to drawing the subtlety. So it could be here. So if you're in the case where you're still okay, so if you're down on this branch here, we know you've got blue and then red and then green. So it's going to end up in one of these two. So you know there's a 50-50 chance of collision on this side of the tree. On this side of the tree, you don't care. You've already collided. So you now have... You've got a collision. So this is the only side that we care about. And so if we go down this side, we have 50% of 75 is 35, so 32.5% or something like that. I think, yeah. How's it? Calculator, 75. Programmers can't do maths. 37.5. So 37.5 and 7.5. So, and this is collide, and this is okay. So down here, we've added 3 things to our thing. There's a 37.5% chance that we're fine, which means that there is a 62% chance that we're not fine. So chance of collision. And so you can see that as as the number of things increases, the rate of which you're going to get a collision ramps up fairly substantially. And so if we do this again, you know, this side of the branch, this side of the tree, no one cares, because you've already got a collision, and this side it's going to be, now we're over here with this one, it's going to be, you know, that either you're colliding or you're putting in there.
Right, so that's 25.
Exactly.
75% chance of collision, 25% chance of okay. That's what you would expect if you had a simple 3 out of 4.
And so once you've added your 4th thing, the odds that we've actually not collided with 4 things, you know, it's not 25%, it's 25% of 37.5%. So
right. Oh yeah. Well, yeah, probably. Yeah, because this is consecutive. probability, like it's cumulating.
Exactly. So what's that? That's please stay in the right place. Thank you. Okay, that's roughly 9.3%, which means that there's like a 91% chance, even though you've got 4 items, 91% chance that you've collided. So this is just working through the
So the birthday problem is calling out the idea that the probability is actually accumulating and therefore a lot less than it looks like on paper.
Yeah. So this is, we'll come back to the Wikipedia page now, and it's like, all right. So you've got a class of what does it say? 23 people. Gives you a 50-50 chance that you've got a collision. So there's 365 or 367. What? Oh no. Okay. I was like, that's not how many days are in a year. There's 365 days in a year, just for simplicity, and 23 people.
That's all you need to get a
50-50. But you add just a couple more people, and so this is the graph. As you add people, it shoots up, and as soon as you hit, you need to hit 367 to guarantee a collision. But all the way down here, like 40 people, you're almost certainly going to collide because you're up above 90% almost.
Right, and I guess they call it a paradox because it seems incorrect.
It does seem incorrect. It's like
you got a whole year, you only got 40 people. How can you possibly have a 100% chance, or close to 100 or 90% chance of colliding?
So it seems cool. Counterintuitive, but this is this is the same logic that applies to hashing. So basically, you need lots and lots of pigeonholes, and you only want to add a few things because the way the numbers work out, you can't add stuff all willy-nilly, I guess, is the point.
That's why we have so many bits of, I guess, entropy or whatever in most of hashing algorithms, just because preposterously sized number of pigeonholes means like a practically useful amount of places of pigeons.
Yeah, so it's like we're gonna hash like, so we can think about this. In fact, we will in a moment. I'll just finish going through this. So the maths behind this, it's actually, sort of, it seems fairly obvious. It's like 365 but then you have to go and like do this business here with the permutation operator and the factorial operator, and it's sort of annoying to write out. Anyway, so this is interesting and worth reading, just for skimming sake, but I don't really want to go through the maths in that much detail. But what I do want to do is sort of think about this from an engineering standpoint rather than a mathematical standpoint. So what we can do is we can say, all right, because we're building a menu system and we're hashing these things, and we, a collision is not going to be the end of the world. Like, it just means the menu screws up, but it is not really desirable. So if we have a simple game, we can think about this like, you've got a menu, it's got some options, we might have sub-menus with options. What would you say the like average number of options in a menu is? Maybe like 10?
Yeah.
So we've got 10 items. And let's say how many menus a game might have? Maybe 20 at a sort of generous estimate.
20 menu screens, like including sub menus.
Yeah.
Yeah.
I think that's pretty reasonable.
Yeah, I think we probably added we probably had like slightly less than 200 overall.
So
menu
yeah,
line
exactly.
in
So
City. Yeah.
200 is not unreasonable. And then okay, so this might just be for like our game that we're making, just one game, but we're making a menu system. People might want to reuse it. So then we have to think, how many games might use this menu system? I should read. So we could say, what do you reckon, like 1,000 games if we put this out as a library? 10,000?
10,000 would be pretty good adoption, I think.
That would be very good. I'm going to say 10,000 is probably less. Like, I think it's more than 1,000, less than 10,000 for a successful piece of middleware. Because I have a feeling that ImGUI has that, for example. So let's just say 10,000 because we want that headroom.
I'm curious though. I mean, doesn't really matter if you collide between games, does it?
This is true. And you're absolutely right. And this is why this is more of a back of the envelope thing. So it doesn't matter that you collide between games, but that does give us more places we can collide. And so think about it, like the actual maths is not so much like, in fact, let's do the maths that way because that's actually right.
Oh well, you never know. Maybe there's like maybe you want all of the games that use your UI system to be able to be played together, like one of those old cartridges that had 1,000 games on it or something. I don't know.
It doesn't actually, come to think of it, it doesn't really even matter if you have collisions between screens.
That's actually very true.
So we've actually got to think about it more. In fact, we actually have a bit of a modified birthday problem because we're actually not comparing 2 million items. We're actually doing this many comparisons of this many items. So we may actually be in a bit of a better state. Now, part of the issue that comes with this is, okay, this is without user input. Now, add users. So the minute that we have basically, like we've been talking about how we have a kick player menu item. What that implies is that we are hashing on usernames, or we could be hashing on usernames. One of these 10,000 games might do something as silly as that. And so, how many users have we got? Let's say one of these games is really successful. It's like 10 million users. So now, this is not so much of a problem. This is a huge, big red flag problem. And not to mention it's user input, so they could deliberately hash collide if they were really jerky. So what we have to think about is not so much this case. Like this case, well, let's do the numbers now. Let's plug this into Wolfram. And let's see if Wolfram Alpha will do the maths for us. Okay, so we're going to use this formula here because it's easier to type. And let's just say we have 2 to the 32 factorial divided by 2 to the 32 to the n. So we're saying we have 10 menu items.
Where did 2 to the 32 come from?
So this is our 32-bit hash. So that's the number of
Oh,
pigeonholes we have. So we've got about
right,
4 billion or so pigeonholes.
right.
Now we have finally. So hopefully you can see I'm copying this one and adjusting it. 2 to the 32 minus n is going to be 10 factorial. That's multiplied, and we'll stick some brackets on here for good measure. That looks correct. Let's see if this actually works. Okay. So.
Uh-oh.
I'm just actually working out, what have I typed in? Is this the chance that it's not going to collide? I think so. Yes, this is a chance. This is, you can see this little bar above it, the probability of not colliding.
Mm-hmm.
So 0.99, in fact, we can go like 1 minus all of this, and it can just tell us what the chance is. So 10 to the minus 8. So we're probably fine with that. That's probably fine, although I'm going to switch back to this thing because it's sort of easy to see. So we've got, what's that, 8 nines of reliability. That's, who could ask for more than that? But let's say now we've got a 10 million player situation. Suddenly, how's our hash looking? Oh my.
Not sure how to read that.
I'm just like, does that even make sense? I think
It's just saying that the chance of collision is basically.
I think we're beyond the knee of that graph actually.
Yeah.
Yeah, we're way beyond the knee of that
Yeah.
graph, I think. Unless I've made a typo. 10.
No, 10 million. No, it looks right in the input diagram. 6 zeros and a 0 for the 10. Yeah.
Okay.
So basically, we just don't have enough holes for that many pigeons.
Yeah, so that
We
feels
busted
wrong.
32
I
bits,
feel like
you know.
I've made a mistake typing that in or something, but it looks right. So anyway, suffice to say that if there's 10 million, if we're doing 10 million hashes and we only have a 32-bit value, at least what we're seeing here tells us that no, please don't do that because you will collide at some point.
Although, who's gonna cycle through 10 million people on a menu? I don't know. Seems unlikely.
This is true, but who knows what we're going to implement. Let's see if we can fix that by changing our hash. Unless Wolfram's made a mistake, that's also a possibility because these are huge numbers. I'd expect Wolfram to get this right, but who knows. So let's say we have a 128-bit hash. And let's see if that can cope. Oh, well. Anyway,
the VM they're running doesn't like that very much.
so this is where you sort of throw your hands up and like, well, we tried. This is probably why the permutation operator is in there or something. Anyway, coming back to the other example, so 10, 10, 10. Oh, sorry, no, 32. So we've got a 32-bit hash. Now let's make it a little bit interesting. Let's say we've got 100 items, just in case there's like a huge menu in one of these. So we've got a pretty good sort of nines situation here going here. Chance of success, but now we have 20 screens times 10,000 games. So what we have to do is take all this. So this is how you calculate this probability, and that is you would say to the power of each game might have 20 screens times 10,000 games. So this will give us a probability that any one game will suffer from a collision without like some stupid 10 million user situation. Wolfram has decided that I am not its friend. All right. Fortunately, that's an easy calculation. So we're looking at 0.999999
Yeah, 5 9
times brackets no, sorry, 0.9999 to the power of what's that, 220 times 10,000 close brackets. So we've got 200,000 games, and so you can see suddenly our chance of success has gone down drastically, because if you multiply, basically exactly what this is doing is doing 0.99999 times 0.99999 times 0.99999. You do this often enough, this probability will go down and down and down and down. And so what we ended up with was like something like 0.13. So there's actually a 87% chance that we will have a collision somewhere.
Yeah.
So you can see sort of the risks of hashing, I guess.
Absolutely. Although I think we already kind of, like, this is a good exercise, especially if you're a library developer and you have to, like, I don't think people spend that much time choosing a hash. I mean, in general, but I think it's important to do that. But I think if we establish that we don't really actually care if there's collisions even between screens or games, then we can probably still just get away with the Jenkins hash.
Well,
and 32 bits. Right?
Well, no. So this is what I'm saying is, like, on a single game, like this is I think you call it iterated, is the correct mathematical term for this. So on a single game, a 32-bit hash is fine, but if on a in fact, yeah. So if we're 0.99999, and then we have 20 screens, this is what we get. So it's still 0.99999. So there's like
right. Why do we care about distributing across all the screens when we only will have one screen active at any given time?
Okay. So let me. I think we've missed a step here. So what I've done is
yeah.
So this
mind.
is I think
we're back to the birthday. It's the birthday. I forgot the whole point of it.
So this is well, no, not quite. So this is birthday, but these two iterated. So they're slightly different. So you can see in the birthday paradox, your odds at each stage go down.
Yes.
In the iterated case, your odds at each stage stay the same. So what we're doing is like, okay, here's our first game, and there's like a 0.99999 chance of success, and then at this stage there's 0.99999 chance of success, and then at this stage and so on. So and then there's the fact.
I keep falling victim to this assumption that is ingrained that because it's only one screen at a time, we're somehow like in control, it's like thinking that your hash has an internal counter, right? And like 0, 1, 2, 3, 4, 5, and so on. And it's like, well, it's not ever going to collide with other screens because of the fact that we're starting at 0 on each screen. Sort of like this data is new, so of course it's not going to collide with other things. But the whole thing that you've been teaching me is that there's no safety inherent in a hash, only the probabilities being reasonable. So which all you're basically saying is that this paradox survives across screens because it's just more math. Like it's more cases where we run into a different set of input that might produce a collision.
Yes.
So, and I don't have this false luxury of thinking that the hashes are deterministic that way, and because they're just not. So yeah, I get it. It's actually just like a ingrained mental assumption about if I control how the hash is created, then for some reason I think that it's deterministic in terms of the data set that I have. So as long as my data set is only used in this one case, then I don't run the risk of a collision. But again, yeah, it's just wrong.
Yeah.
We're basically saying we're iterating over these 20 screens and 10,000 games. It's just giving us that many more chances of running across the paradox in that set.
Exactly. So 6561. So you can see hopefully what I've been drawing right here is, so this is the iterated one. So in the iterated one, the probabilities at each stage don't decrease, so it's not as catastrophic as the birthday paradox.
Right, but you've still got loss, I guess, because of
exactly. So this is it with 0.9, which is like quite extreme, just for the sake of example. So even after 1, 2, 3, 4 iterations, we're almost down to 50-50 with 0.9. So this is like it's kind of like thinking about you remember O-N sort of notation and stuff.
Yep.
And so if you've got like O, well, what would one of these be? This one, for example, is 0.9 to the n. No, it's actually... How would you do this? I think... yeah, you just call it k to the n. But as you can see, when you have like a O n squared situation, once you get above here, your n has to be really super low, or your ability to handle this, as in the number of bits you have has to be really high. But seeing as our n is quite high, it's 200,000 roughly speaking, our k has to be right. This is not a great example because it's where probabilities go down whereas operations go up, but you sort of get the concept. It's like we want to keep our k quite low here because we're iterating. So 0.9 is obviously not enough, and we found that 5 nines, those extra nines, we also found that wasn't enough, because we got 0.13. So if we have like 0.999999999, and then we do like let's see if this is gonna do us. So yeah, so if we have enough nines in there, we're still pretty good. So you can see sort of how these two problems interplay with each other. So if you can reduce this one, you're good. If you can reduce this one, you're good. But to reduce this one, you have to add a lot more bits to here. So that is sort of a really long-winded way of saying
we need a 128-bit hash.
In a real-world situation, we actually do need at least 128-bit hash to be fairly safe on this one, because we can't really control the number of iterations. If like this gets released as a library, someone's going to get a collision.
Right.
I mean, you could say, well, we don't care. There's that is technically an option, but seeing as we're professional software developers and we
we're building a library, which is like the one case where you are you're okay with scaling.
Certainly, yeah. So it's like if this was for one game, you'd probably have stopped by now because you'd be going, it's like, all right, I need to work on something else. But for a library, you'd spend a bit more time. So the other thing that I wanted to do a quick revision of, so we implemented the Jenkins hash function, and we sort of talked about some of the bitwise operations to make sure that we've got a fairly good handle on what those are. So not only did we implement Jenkins, we actually did a bit of stuff to pull bite-sized 8-bit values out of a 32-bit value, because the Jenkins hash is sort of byte-oriented.
Yeah, I remember we were doing some operations to take off the top 8 bits and shift down to the bottom so we could represent it in 8-bit chunks instead of 16.
So I just wanted to quickly run over. So we had a few operations that we wanted to look at, and we covered this last time, so I'll just restate what they were. So we've got, say we've got, needed more space. Okay. So say we have, so an interesting thing that I learned a long time ago is humans are very good at dividing things in two accurately. Other ratios, not so much. So say we have our bits and we wanted to shift them. So we've got bit shift, sorry, we'll start with right. So if we have bits here and we shift them right, we end up with say we shift them right by like 2, we end up with them here.
Sorry, when you say shifting them right, did you or did you not just shift them left?
I have been saying right when I meant left. You're correct. Quite correct. Yes.
Well, I know I don't know anymore left and right when I do these things. So.
Yeah, I really should know, but yeah. Okay, so bit shift left. It's the one that makes the numbers bigger. So what we've done here is we've done shift by 2 to get to there. I should really be doing like this so that it's quite clear that these are not zeros, they're just arbitrary. And so one thing that this will do is this is equivalent to doing how would you write this? It's equivalent to doing multiplication by 4. And do you understand why that's the case?
Well, I'm trying to think of it in terms of binary, like the 1 bit and then the 2 bit.
Mm-hmm.
You've shifted them 2 times, but I don't actually know. I thought it would have been multiplied by 2 because of the 1 times 2 being 2, but I'm clearly wrong. So I mean, I get the idea that of how they're moving and where they're getting the values from, the decimal values from, but I would have just like 1 becomes 2, so that's times 2, and then 2 becomes 4, so that's times 4.
So okay, so this one here, this 1 goes is basically going from the 1 spot to the 2 spot to the 4 spot. So
well, that's all there is to it then. Yeah, 1 and 4. Yeah.
And then the same thing by the same token. So the 2 value 2, 4, 8. So 2 times 4 is 8, and so on. So and you can calculate this. It's basically for shift left. N is equivalent to multiply 2 to the n. So and I'm sure you've seen, like, we've already done this a couple of times, like 2 to the n comes up a fair bit when you're working with bits relative to each other. Okay, and then we have shift. Now we're shifting right. Now, so let's say we have, let's go with pink. Da 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 da. And then we want to shift it to the left by, say, I want to do this slightly differently, actually. Let's do this A, B, C, D, E, F, G, H. Okay, so say we're shifting this to the right by 2. There's actually drawing. da, 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 da. There's actually two possible ways we can do this, which I think we did cover. So shifting right by 2 is obviously fairly straightforward in this sense. B, C, D, E, F, A, B, C, D, E, F. Now the simple thing to do is, just like we did over here, is we introduce zeros. So we could go 0, 0. But we could also do this. So this second case is called, it's got a proper name, but this is like unsigned, and this is signed. And the proper name for this one is sign extend. So as you know, this top bit is the sign bit. So if this is an unsigned value, you've got 1, 2, 4, 8, 16, 32, 64, and then plus or minus.
Right.
I don't really want to get into the vagaries of 2's complement, but basically the nice thing about 2's complement is that the numbers, when you shift them right, look like they fill out the space. And we can see this in calculator, and I think we did this example last time. So if we have a dump, can I have my calculator back, please? I've got like a million instances of calculator open. That's the one. All right. So if we have a bite-sized value and we stick in like that, and you can see that this is negative. So, and the negative values, like, okay, so this is -2. You can sort of like, this is a bit wishy-washy explanation without going into how this is calculated, but like the negative sign sort of fills all the way along to where you actually have the value. So if we have the thing that I entered before, and we're going to shift it right by 2, you can see what happens is it fills in a copy of what was there. So if by the same token we have the same value, I think it was that, and then we shift it right by 2, this is the same operation, but there's a 0 to copy, so it just copies in zeros. So this copies in the sign. So this is why it's AAA. It copies through the sign bit. And that basically tells you that this is equivalent to division by 2 to the, sorry, well, this is by 4. Division by 4, so this is shift n is equivalent to division by 2 to the n.
Okay.
And so, and then when you have signed values, it works like this. When you have unsigned values, it works like this. And it's also, this is integer based. So when you like do 2 divided by 4, you get 0.5. So you actually, you've got G down here and H down here. So you've got 0.5 and 0.25 is what these places would be if they were represented. They're not represented, so we just kick them off and we effectively round the value. But you can sort of see how this, if you change the interpretation of these things, like if you pretend you've got another byte here of stuff, this is how we implement fixed point as well, is we just pretend we have smaller and smaller places in the bits.
We wouldn't. I mean, I think it's useful to know like what the shifting is equivalent to in terms of decimal representation, but I don't like. That's not why we use it though, right? We don't use we don't like when we multiply for 4, we don't try to left shift by 2. Like we care because we're able, like I guess the value of this is being able to actually, well, the whole point is called bitwise, right? So in other words, being able to manipulate these at the lowest level, like the bit level, gives us more flexibility for like for operations, right? We don't really think about this in terms of decimals, do
Well,
we? I mean, is it important sometimes to use this for multiplication and division, or no?
well, when we're doing fixed point maths, so you'll remember our fixed
Mm. Yeah, fix
16-bit.
655
That's the one.
436. Yeah,
Yeah, that's like I don't remember that number.
it's burned in my brain.
But yeah, we had to sort of think about how do we convert between the two number systems, like what, like basically every time we do an operation we're multiplying by hang on, 2 to the 16, yeah, 65536.
Oh, 536. I said 65436.
Yeah,
I missed one number.
so we could have implemented this just by multiplying by this number and then dividing by this number, but the reason we do it this way, of course, is it's way faster to do a bit shift. Loosely speaking, there's some
You mean
situations.
like intrinsic SIMD type stuff? Like CPU can do bit shifts faster than any kind of math operation.
Multipliers have traditionally been quite slow, and shifts have been traditionally quite fast. If you have a piece of hardware called, is it a barrel shifter? So here's a real fun aside for us. Let's say we have, God, how many?
What have I done?
let's say that Andrew sort of can be bothered. These dots represent memory locations, and 2, 3, 4, 5, 6, 7, 8. So say we're implementing a CPU, and we want to implement a shifter. So there's two ways we can do it. So are you familiar with the term, oh God, ALU? Have you heard of this term before?
In my digital design class in computer science in 2000X, I don't remember. But yeah, I don't,
Yep.
not anymore. No.
So it's an arithmetic and logic unit. So this is the part of the CPU that like actually pushes through the thing. So there's two ways you can implement a shifter. One way is you can do it like this, which is basically da, 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 and then you'd have basically a wire running there. That would go nowhere, and you'd have a 0 coming in there. You can imagine if this was doing this kind of shift. Oh, actually, no, we are doing a right shift. You can imagine, depending on whether we're signed or unsigned, we could either do this, and we've got a bit of logic there. Just ignore the fact that this is not a sensible diagram of a circuit, but you can imagine this is like the enable bit for signed versus unsigned. So either we're copying this one or we're copying a 0 into this memory location, and then you just have, let's do colors. You'd have probably a enable coming through there that turns on this circuit that basically does this shift and just shoves all the bits one to the side. And you can imagine like there's a whole lot of other circuitry with its own, enable for add, minus, blah 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 blah. Enable, what's that? That's right shift. Right shift, enable, sign.
Completely mind-blowing that this is all electric current running through circuits
Oh yeah.
to make all these numbers flip from 1 to 0 so that we can do this session over the internet. It's completely insane.
Just imagine how many billions of these shift operations it probably is doing just to wiggle this cursor around.
Yeah.
But okay, so you can see that this is fine. This doesn't take much space on the on on the screen on the circuit board. But the problem is you're only shifting one place, so you have to then go and implement some sort of loop. So that will then, it's like, okay, here's our, loop, shove it back into the input, and you'll count down. So if you're doing if you're doing shifting right by 2, you'll do that once and then you do it again. If you're doing it by like 6, you got to do this a whole bunch of times. So you're wasting a whole lot of cycles doing this. The other way to implement a shifter is let's do it like this.
You call this one a barrel shifter?
I think is it called a barrel shifter? Let's ask Wikipedia.
It sounds like a steampunk weapon that you find in a wasteland somewhere and then soup it up.
Actually, I'm hoping Wikipedia has a diagram because I don't really want to draw out a barrel shifter, because the problem with the barrel shifter is it's much bigger. So what happens is da 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 da, and so on, dot dot dot, and then you have you've got the enable line for 1, and then you've got the enable line for 2, and then you've got the enable line for 3, and so on. And so you just say, all right, I want to shift by 1, I want to shift by 2, I want to shift by 3, and then the shift is here's one space shifted, here's another space shifted, another one. So it's basically the same as this, but you have a whole lot in a row.
Right, it's almost like iteration versus recursion, right? But at the circuit level, you've got one that's designed to do n number.
Well, it's actually more like an optimizer. It's more like loop unrolling.
Okay.
In fact, it is, because you've got a loop here and you're unrolling it, so you're just laying out that many copies of the hardware.
But it has to be physically there, right? It's not loop unrolling in that sense, right? Because you have to actually have these things literally. Isn't the ALU you're talking about physical things right now, right? The innate circuits, you have it all laid out. Doesn't that mean that there's only there's a fixed number of, in a barrel shifter, there's a fixed number of shifts it can do, right? Without looping.
Yeah.
Right. Okay.
So I'll bring over the Wikipedia because this is.
Sure. I mean, we're over time, so you don't feel obligated.
Oh, we're not that far over. We're not over time, are we? No.
Yeah.
Because we started late.
Oh, okay.
But still, I'll I was going to do some coding today, but I think we'll save that for next time. But I did want to cover this all this bit stuff. So this is what a barrel shifter looks like. You can see they sort of design it so going in and out the side, so you don't have the problem that I have here, which is it's all going top to bottom, which is not. I mean, actually, I think they do actually implement it top to bottom effectively. What I want is do you remember we looked at the Visual 6502?
Yeah, a long time ago. Yeah. Yeah, I remember. Jeez.
Somewhere. Is it the 6502 or is it the was it the Z80? Because I just want to actually. Alright, the 6502 will do. I'll see if I can find it real quick. It's a PDF. So anyway, over somewhere in here we'll be able to actually see that circuit, and you'll see that from memory this is okay. These are the okay, so this is, let's just go through it. So this is decoding instructions. This is all of the logic is what are those instructions going to do? And then down here we have registers. I think these are the registers. It goes one way or the other. I'm a bit confused. I think this is the ALU. God. Something like that.
Somewhere in here, there's a barrel shifter.
I think the 6502 has one. I'll be embarrassed if it doesn't. But anyway, so stuff comes out the registers into the ALU. Some ALU is vaguely here, and then comes out and just gets routed back into the registers.
They literally had to make these one at a time back in the day. Like they soldered them together.
Well, I mean, yeah, you actually could do it that way for simple chips. In fact, chip design was a very manual process. Like they drew it out like that. I think that's a transistor or set of transistors, and then they cut out the was it lithography?
Right.
So they cut out the different transistors that then project through a series of lenses onto the tiny bit of silicon.
Nuts.
Okay, so here we go. Registers, ALU, instruction decode. So there's sort of the logic for that. Can you give me just a map of the chip? This is actually, yeah. So this is the registers in the ALU are down here. I know exactly what the picture I'm looking for looks like, and
They emulated the actual chip. That's crazy.
yeah. So it's like a not quite. I don't think it's an electrical simulation, but it's like a digital simulation. Like that transistor's on, that transistor's off. Like if I come over here and hit play, you can see it's turning on and off different things. Anyway, I won't belabor the point any further. I think you get the idea. You can see, so it's writing to memory. It's activating different pins on the chip. It's doing stuff in here. So you get the point. That is how shifts work. In fact, that was a digression. That was complete.
No. But I mean, I caught the main point is that the barrel shifter doesn't require any actual logic. It's just basically combining those bits like directly, so that it makes sense that it wouldn't require as much work because there's no thinking involved there. There's no logic. It's just shifting, literally moving electricity over or whatever.
Well, let me try and.
I dropped out of digital design, so
Let me try and work that into. So it literally says here. I think I skimmed it without using a pure combinatorial logic. So it's like.
It is logic. Sorry, I guess.
Yeah. So it's like.
I think sequential versus combinational. That's it.
Yeah. So these are the enable lines for like. All right, we're just going to move the bits around into different positions depending on what line is enabled. Whereas,
Right.
Here's what I'm after, a binary multiplier. Let's see if it's got a diagram. So here's like, so you can see.
Or gates.
This is using like, it's probably not even, it's a gate of some description, let's say. And it's using one of them per bit, per potential permutation. Whereas this is like, here's a 2-bit multiplier. And so you can imagine if you've got 32 bits, you're going to need 16 of these units, which have got all of these things. And then you have to deal with, that's 2 bits. So it actually has a problem because you've got to then move the overflow around. So this is actually, you can see why they don't have a simple diagram here other than the one that's for 2 bits only, because it's much more complicated. So it's more power. If it has to do things sequentially, it's more cycles and so on, whereas this is really simple. It just uses up a lot of surface area, relatively speaking.
Right, that's the trade-off then they're making.
Yeah. And I wish I could find it. I think I've closed it. So anyway, we'll there's reading the 6502, and I think they've got a Z80 or something through their like talks and stuff. You'll find that diagram somewhere, I'm sure. It's interesting. Anyway, so just to finish off, so those are the bit shifts, and that's sort of all we need to say about them. The other operations we wanted to talk about were we've got and. So if we have, let's go down to however many bits that is, A, B, C, D, E, F. So if we've got an and, say we want to just mask off the lower bits, 1, 1, 1. Oh, let's do a different color so I can see it. 1, 1, 1, 0, 0, 0. And so what we get out the end is 0, 0, 0, D, E, F. So you can see how and is useful for, like, I would like just these bits, please get rid of the other ones. And so
yeah,
I think we wrote down last time.
yeah, that was the one that
Mask.
I picked every single other operation except and when we were doing it the first time through. I do remember that.
So and then we have
the combiner.
We have basically the combiner. So let's say we've done that. So we've got D, E, F, 0, 0, 0. And then we have orange. We have Q, I won't use Q because I've got the zeros in there, X, Y, Z, excuse me, and then we've got, that would be 0, 0, 0. So say we've already masked these values, we've shifted them around, perhaps we shifted this one up by 3, so it's out of the way of that, and then we do a logical OR operation. Combine, and so we obviously get X, Y, Z,
D, E, F.
D, E, F. And you'll recall I showed you the color thing, which stores it's a 32-bit color value, and it uses these operations to combine it. So it's got 8 bits of alpha, 8 bits of red, 8 bits of green, and 8 bits of blue. And they're all sort of in this 32-bit structure.
Yeah, the packed vector.
Exactly. And then the final one is exclusive OR. So that one, so let's just take, let's do it this way. So we've got A, B, C, D, E, F. And we want to XOR with something like 1, 0, 1, 0, 1, 1. Our output, and this is how we draw these things, is going to be the inverse of A, B, the inverse of C, D, the inverse of E, the inverse of F. And so that's sort of how those things work out. Does that, like, I've sort of skimmed over this, but obviously, so if this was 0, this would be 1. If this was 0, this would be 0. If this was 1, this would be 0. If this was 0, this would be 0. If this was 1, 0, then this would be 0, 1. So
right, it's exclusive. It's exclusively OR. Yeah, it's like the only ones that show up as ones are going to be the ones that were one or the other. In other words, 0 and 1 or 1 and 0. Selective inverse.
Selective inverse OR. Overlap combine.
Overlap combine.
So, like, you're combining two values into the same space. So we've sort of taken whatever this is, and sort of munged them together into a single value. And so this is why you see this come up in hashes a lot. It's like we've got 2 bit patterns. They're kind of arbitrary. Let's get another arbitrary bit pattern out of them that is a combination of the two. And we're combining all of that information.
Right. You called this distributing at one point.
Did I?
Distribute bits. To distribute bits into an array or into the hash.
That sounds about right. I'm not sure I'd say distributing.
Well, I could have got it wrong. Yeah.
But it's sort of that. It's along those lines. Like, I think what I would say.
I call it the smart one because it's the one that you usually use to do something maths oriented.
What I would say is I would call like this whole operation like distributing. So we're putting a whole bunch of new bits into the hash, and then we're like shuffling it around and making sure it's covering the entire hash effectively. So that's sort of a review of the maths that we did last time. Is there any questions about any of these things?
No, I feel like I followed that. I think
Oops.
I think for me getting practice with like fluid, like a fluency of like using it in programming is the next step. Like
Yeah.
we did this with the with the Jenkins hash, and that was useful to like when we were going over like the optimization of it, and I that's probably where I would need to get it under my fingers, so to speak.
So what I wanted to do is so we've established two things. One is we probably need a wider hash, just for
Yes.
safety, and we've covered.
Could we make Jenkins into 128-bit hash? Can we just do it against like 4 values, or doesn't work that way?
I'm a little bit. Is there a wide version of Jenkins hash? Spooky hash.
In general, I guess it's not. Yeah, spooky hash, right? That's what you were saying.
Yeah.
But it's in general, it's not like you can't take an algorithm for 32 bits and just sort of like make 4 of them, like a barrel thing. Like and then just like do it. Like you can't do that. Just fundamentally, it has to be a different algorithm.
Okay, so yeah, we can't just expand out this. There's just the basic Jenkins. I don't have a basic Jenkins, but we get the idea. And we can't just expand
out. You can't sequentially. Yeah, I was thinking like, why not just take? Well, you used to do it in like one time. We'll do it 4 times, and then just take 4 bits at a time, and put them into like all 4 spaces of the, each 32-bit chunk of the 128-bit array.
So you can imagine. Okay, so where the Jenkins output is 32 bits, and
right.
So what we're doing is we're taking 8 bits for each of these block operations, and we're trying to take these 8 bits and shuffle them up and distribute them. This is, I think, where I'd say distribute them into the hash value. And roughly the idea is if you change, I wonder if this even applies. Yeah, one bit of input, you should, in theory, change 50% of the bits of the output.
Right.
And the idea behind that is it loosely speaking means that you are not really predictable. It's a rough way of saying it.
Right. Well, you said a good hash root is somewhat equivalent or comparable to a random number generator.
Exactly.
Right.
So let's say we took this 32-bit hash. So we're taking 8 bits and distributing them into 32 bits with each of these operations. So if we expanded this out to 128 bits, we would need to come up with the right combination of addition, XOR, shift, and maybe other things that would properly distribute these 8 bits now into 128 bits.
Which is basically what you'll tell me is essentially what spooky hash is.
Well, it's really what all hashes are. So the thing is, like these 2 operations, and I guess this one, so 1, 2, 3, 4, 5 operations have been designed to do this well. And so it's like you have to pick your operations, pick these numbers, and then we come down here. We also have this avalanche stage just to mix up the bits in the final step. And again, these 1, 2, 3, 4, 5, 6 operations and these 3 constants again have been designed to work on 32 bits. So if we wanted to expand this out to 128 bits, we'd basically be coming up with, a 128-bit avalanche and a 8-bit to 128-bit insertion, or possibly because we've got 16 bits here and we've got 32 bits here, we
might be 16 to 128.
Yeah, 60. Probably we would do 32 bits to 128 bits, just for sanity. But it's not as simple as just 10 times 4, like, to expand that out, because obviously you can imagine what would happen is if you insert,
you're not getting away from the collision. Yeah, you're just basically
inserting more zeros. You're not actually adding, I guess it's not really entropy, but adding randomness to the situation.
Entropy is just for, I guess that's the cryptographic term for adding bits of junk.
I guess so. So this is why, I've got a rough understanding of how these things work, but I've never implemented a hash function of my own, because there are people out there who have sat down and done the research. So what they tend to do is I'm pretty sure the way these things usually go is they just prototype a whole bunch of things and run it through a whole lot of data and see what works out best. That's how you come up with values like these and a particular order of these operations.
That's speculative almost, like.
Yeah, like I think, again, because I've never implemented one, I'm not entirely sure, but I think the way these things tend to go is like, I got a feeling, I'm not getting enough bits at this stage into the right spot, so maybe we'll try that and try run the things again. Did it get better? Did it get worse? And so on. You can also imagine they might do perhaps an exhaustive search for, like, what are the best constants for this set of operations to give a good hash. And in fact, we saw that. Did I close that window? I did. Let's bring it back. We saw a little bit of that over on the Jenkins Hash Wikipedia page, and that's like, this is the avalancher. Look at that. It's not clumping up. You don't have any unfilled pigeonholes, and you've only got a few. I'm pretty sure what this means. There's just bits effective. Yeah. So it's like, it's got good mixing behavior. So it's just really roughly speaking. There's a tool called I believe it's called SM Hasher. Here we go. So, test suite designed to test the distribution, collision, and performance properties of non-cryptographic hash functions. So, this is basically a test suite. So you can imagine that, if we wanted to design a hash function, we could compile this thing, and they've got Spooky in there, they've got Murmur, they've got various versions of Murmur, and so on. And so we could go in there and be like, all right, well, here's our hash function, test it on your data and see if we can get better behavior. But that's one of those things. It's like, are we sufficiently mathematically inclined to beat these guys at coming up with hash functions? And it's like, well, probably not.
No, sir.
And particularly, like, we were talking, because when we started this, Casey was still tweeting, and he's probably still working on Meow Hash. And it's like, well, has he got the graph in here? Maybe the graph is on here. It's like, you're not going to beat Meow Hash because it's just using the AES instructions to get the shuffling. So it's like,
right, although that makes it not that portable, right, in terms of a hash function, because it's relying on an instruction set of being there on the CPU. Like, normally software for hashing is cross-platform enough that we wouldn't need to know what the CPU can do, right?
Well, I believe, there's a certain, like, the whole idea of non-cryptographic hash functions is they're very, very, very fast, which is why, it's like add, shift, XOR. Like you don't see it like a multiply or a square root or something ridiculous in here. And it's just a handful of operations. And of course, both Intel, like even fairly old Intel CPUs and also even fairly old ARM CPUs do have that AES instruction that Meowhash relies on. So I've sort of skimmed the source code for Meowhash, and it looks like last time I looked, there was like, once we've figured out exactly what this is going to be, someone will go in and write the compatible version. It's like, oh, you don't have that on your CPU. You can run it on like, your little microcontroller or whatever, and it's just going to take forever. But you can still calculate it without that CPU support.
Right.
So,
I see.
But it is going to be slower in that case. But seeing as there's experts on the case.
Yeah, absolutely. I mean,
like,
and also, I mean, it's useful for specific use cases too, right? I mean, isn't it? That one is optimized for content pipeline.
Well, Meowhash is like super, super fast because it's
right, but you couldn't write like a .NET version of that like in managed memory because you don't even have access to that level of the.
No, you couldn't issue
AES.
Yeah, you couldn't issue those instructions, so you'd have to interop out to native code.
Right.
But that
in which case, then, yeah. Sorry, go.
I was just going to say, but then you'd be just as fast minus the interop costs. So you can imagine, like Casey was doing a lot of work to get the hash times for, like, say you've got 8 bytes of data and you want to hash it. Doing all the setup stuff that he was doing for such a small number of bytes originally was relatively slow compared to like just slamming it through something like this, perhaps. I can't remember. Like, there's a graph somewhere. I think it might have been 20.
Oh, right, but then he did the work to make it work.
Yeah, so he did the work, and I think Jeff from Rad Game Tools was involved, and possibly some other people. It's like, hey guys, if you want to make this redonkulously fast, here's how you do it. Which is good. But if you then interop to it, obviously interop as the core overhead cost, because .NET, and you can get rid of some of that. What is this? Suppress unmanaged code security something.
Right. Yes, but I mean, I wonder if there's. I'm just curious if there ends up being a hash or a function that is faster in managed code because of the interrupt costs to going native, or whether that's still going to be. I'd be curious to see whether like Meow with interrupt is still going to beat like most of the other ways to do it in the .NET world.
Anything, yeah, it will. Anything over, I don't know, a handful of bytes, let's say, which is the sort of the design purpose of Meowhash, is like content hashing very quickly. You'll quickly overcome the interrupt cost, because what it's going to be is like, all right, I've got a block of managed memory, pin it, call into native, let it cycle a bit, get the hash back at the end of it. That's going to be very, very fast.
Right, not a high complexity for interrupts. Literally just calling the function and getting.
It's just one call, exactly. So it's like, and that's sort of the thing you accept when you work in managed code. It's like, all right, if I need to interop out, I can't just issue CPU instructions directly. Like, you can imagine, like, if you really, really cared, you could, I don't know, maybe write some plugin to the JIT or something. I don't know, but yeah, you could do it that way. But
maybe with Roslyn or something. But I wonder if but then I mean, if you have to go into native code, then you're carrying with you a bunch of native code, and then you have to worry about what CPU you're compiling to.
This is true, and this is why
it's not fun for the maintainer of said library to interrupt.
Well, yes and no. Like, I'd, I'd love a world where I guess you'd have to worry about ARM versus x86.
Yeah.
Um, but yeah, no,
Yeah, that's why I would use like XX hash, which has managed implementations and is
yeah,
plenty fast.
yeah. So it's like, what are you hashing? Like, we're hashing strings. So at some level, like, we really don't care. Um, so and so we wouldn't do the work, but we might do. Well, no, we will do the work. So the plan for next time is we're going to grab murmur hash and we're going to implement it. So here it is. It's it's a fair bit longer, and it's got some function calls and stuff. But we'll implement that and have a bit of a practice of doing various operations, and talk about what they mean.
All right.
But yeah, you wouldn't bring in all the complexity of that for doing strings. But if you were doing content in a content pipeline, you would definitely want the speed because, like, for exactly the reasons Casey wanted it.
Yeah, absolutely. But what do we do in our River City? I mean, the content is using murmur hash now.
Yeah, it's using murmur hash and it's fast-ish, but keep in mind the River City assets are retro resolution, so there's not that much data. You can imagine if we had like full screen painted textures, that would be what, like 8-12 times the size roughly.
Oh yeah, that would be chunky. It isn't. Yeah, I mean it's good. It's pretty good performance, but you do notice when you're doing a full content build.
Yeah,
that's for sure.
A lot of that I seem to recall is just OGG encoding the sound effects because the OGG encoder is quite slow. But
right. Although we haven't. Yeah, we could have switched to a different thing. I think at this point, I think the F audio FNA might be faster, but who knows?
Well, we've still got to encode.
Maybe it isn't.
No, we still. It's the encoding step because you still have to encode it. We've already switched to F audio's built-in thing for playback, but it doesn't have an encoder.
Right. Yeah.
But I seem to recall something like 30 seconds to encode the sound, and then like 2 seconds to encode the graphics. So
interesting.
You can sort of see where the trade-off is there. Sound is weird like that. But yeah, and you can almost see that, like if you look at the size of the input directory, it's like sound, all those WAV files are actually huge.
Yeah, the vast majority of the size on disk is audio. I think it probably even eclipses like everything else, like the code and the graphics and everything else in the game.
Yeah, because how much sound have we got?
Like 200, like 200 megs, I think, or more.
Have we got half an hour of soundtrack? I can't remember how long the soundtrack is.
Yeah, about that.
So let's say 30 minutes times 60 seconds in a minute. So we've got 1800 seconds times 44100 samples per second. And are they 8-bit samples? Or
no, they're more than that.
I think they're 16-bit.
They're more than that, yeah.
And that looks about right. So yeah, 158 megs of audio.
Right. Yeah, and like I think the entire package is like 200 megs. So there you go.
Yeah. So that gets quite large. Whereas graphics, we've got probably about the same amount, but then the OGG processing is quite strenuous compared to just the very simple run length encoding we did on the graphics.
Right on.
Okay, I think we're now slightly over time. So let's wrap this up. If I can find OBS. All right, thanks for watching, everyone, and we'll see you next time.